Hear me? You hear this okay? I want to thank you guys for inviting me to the cargo pants and messenger bag meetup. How you doing today? So this is a talk about reverse engineering executables, and I'm going to try and talk to an audience of people who know something about computers and some people who may not know so much about code in computers as well. So just bear with me. I think you'll enjoy this. The GitHub for the example code is up there. And the nice thing about this is this presentation is available for share. So anything that we do here in the videos that are on YouTube, you can all get to them from here. The first page has the actual presentation. So like I said, I want to kind of start out with how do things work from a high-level view, and then we'll go on from there. I'm a developer by trade, so I write code, front ways, right? From the source code, and you get an executable. A lot of people use executables, but they may not know how that they were written. I think it's helpful if you're going to reverse engineer them to know how to write them, right? You can see what they're doing. And so basically, a programmer writes source code in a high-level language. You have a compiler. He generates an executable. You've all seen an executable. And what is the executable? It's a file. It's a special type of file, which is a sequence of instructions. Then kind of level set. All right, so here's an example, and we're going to use this example a couple of different ways. And my goal is to say, like, source-wise, this is what it looks like. Debugging it with symbols, this is what it looks like. Then debugging it without symbols at assembly. And you can kind of see from doing this, it's going to be difficult. So what are other ways that you can get ideas about how code works? It's not just having to go to the assembler to figure it out. And we'll have some stuff there about presentation with static and dynamic analysis. So anyway, this is a C code, and when I showed this to a friend of mine here, he was like, "I don't even know what this is." And I thought maybe everybody would, but you may not. This is very simple. There's a routine here. It's main. It has a variable declaration for 3 variables. You have a I equals 1, J equals 2 for initialization. You have a sum, which is the third variable. It takes the result of a function that has 2 parameters. And then you're going to print that sum. And this shows a very simple program, but with this, through the debugger, you can kind of see what's going on. And I encourage you to, if you're going to learn with something that's very small and simple so that you can expand from it. So we're going to show this a couple of times, but this is it. One thing you'll hear me say is talk about strings and format specifiers. This is a string. The %d is a format specifier. The printf is a library call to send something to the screen. So it's going to literally say sum equals, we're going to replace the actual sum variable with this format specifier. So, the big picture. You have instructions, functions, registers. You have a machine state, memory, and programming constructs. When we're going to talk about registers, and when I was showing this to my friend, he was like, "I don't even know what a register is." And well, the thing is with a register is, you know what memory is, right? Memory is like a big address space. It has like a lot of locations. You have an address. You have a place you can store variables. And it's off board the CPU. The CPU itself has the same kind of thing. You have memory storage locations, but they're much smaller. And because they're much smaller, you don't actually have to have a big address to register it. You can have a name for that register. And so we're going to show that. So, and we talked about instruction sequences. So here at the lowest level, this is an assembly instruction. It's like move long. You have a constant and where you're going to be moving it to. This is a base pointer. This is a register within the CPU that contains the address of where you're going to put something with an adjustment outside. So if you look at that executable, that text file, or that executable file, which is the file, right? You can use an octal dump program on it, and you can then say, hey, I want to see, this is the file name, by the way, what that thing looks like. And sure enough, you're going to see these two instructions corresponding to this opcodes. However, that's kind of difficult. Like, the computer has to use, a program. If you're actually in the computer, it's doing it, trying to do the decodes based upon what it's going to do. If you're in a debugger, pardon me, or a disassembler, it has programs it's going to use tables to look up how to build these. If you're doing them by hand, you could flip through an actual instruction set manual, and you can say, okay, well, if it's this byte, and I'm going to be doing this offset, you can actually do it by hand, but it's difficult. You don't really have to worry about that because you can use tools. So this is a slide that my friend was saying he thought was kind of a little obtuse. These are the names of some of the registers. And there's a whole bunch of them. I never know all of them. Sometimes I was like, oh, what do they do? But it's nice to be able to recognize the base ones and what they're used for. Really, the most key thing here is the EAX register. EAX in Intel assembly is your accumulate register. There's a lot of instructions that use it as your result. Function calls typically send a result there. Continuing, these are some more of the registers. Here, I think the most important thing is the base pointer and the stack pointer. These two registers are used primarily to handle how you go from one function to the next. And it's using a stack frame. Maybe you've heard of that, crashing the stack. Well, we're going to show that. So I think this is a key point to understand. A function call is performed when the caller pushes function parameters on the stack, and then you execute at that instructions, and you get back, and the base pointer is what's actually maintaining the frames. So here's the stack frame. Remember, the base pointer and the stack pointer, those are instruction registers. It's typical to have your memory accessed from high memory to low memory. Your base pointer is pointing to your old base pointer so that you know, like, if we were to take this and put back in the base pointer, we would be down here someplace. The return address is when you call a function. This is where you're going to return to. The function arguments are like, you're going to put these things on the stack and the return address and the frame pointer before you start getting into the function, and the function will start putting the local variables, which will maintain via the stack. And don't worry, all I'm trying to show you is here is like kind of like the big picture, because I've got some next slides which are kind of cool and I think you'll enjoy. By the way, that was for x86 32-bit, which you can't even get a 32-bit machine anymore for x86. 64-bit's a little different. So I'm going to show you that there. Because they have a lot of registers, they have more registers than 64-bit, they can do things differently. Stack frame exit, so after you call a function, remember I said your EAX register contains your result. This is kind of what you're going to look at, same kind of thing, high memory, low memory. Once again, local variables are above your base pointer, and return addresses are below it. All right, so everybody wants to do a reverse engineering for Windows, but what I'm going to do is I'm going to do this at first in Linux. I prefer it. It's a little bit easier. It has a little bit of a syntax difference, namely, Linux was System 5, that was from AT&T, so they use System 5 assembly notation, versus Windows is going to use Intel. Nice thing about this is your source and destination. They have a little bit different syntax. Percentage is meaning your register. We saw this before. A $sign is a constant, and brackets mean an address. I'm going to use a thing called GDB. GDB is a GNU debugger. If you set up an init file, when you start it up, it will do these things. But you can also, if you're so inclined, you can set the disassembly to Intel. So instead of like looking at it as System 5, you can do it the other way. And then here is just something very simple. I'm showing you that the GDB and the program files, I'm going to set the args, the executable, and particular addresses I'm going to break at. And then here's how you would start up a debugger for a program. I'm going to use the text UI option so that I can see the source and the registers at the same time, or possibly the assembly and the registers. I hate every time you see someone talking about GDB, they simply show you a bunch of commands. I hate to do this to you too, but if you're trying to pick it up for the first time, if you can know these instructions, you've got a pretty good experience of what's going on. Disassemble actually does that. Disassembles, it disassembles from an address. So here is this, what? Yeah, well, okay. I think these slides are the best for this particular topic. They're animated. It took a lot of time, and it was kind of odd. But basically, what I'm going to try and show you, if you remember that code before, you're inside of a very simple. We're going to have 3 variables. We're going to have a I equals 1, I equals 2. We're going to do an assignment via function, and then we're going to come back out. We're going to print it out, right? So this is like trying to show you what the code looks like from the assembly level and what the frame looks like. So this is the frame, and if you remember, we showed those slides before. This is your instruction sequence. So this is the a line of code, and this is an address. I don't have the actual opcodes being shown. That's not important to me. What's important is what's the assembly line doing. And then down here, I'm going to set up that periodically I'm going to look at the base pointer, which is, remember, the frame, and I want to offset it by 32. And the reason I'm doing like 32, in reverse is because I want to see as it's putting stuff on. And if you remember the high and low memory addresses, so this gives me a good range over here. And I'm going to kind of show down here at the bottom the results of the registers. Remember I said like EAX, EBX, these are registers within the CPU. So let's see what happens here. Let's click some slides. So we're going to start off, this is your instruction pointer, this is your stack pointer, this is your base pointer. This particular instruction, he's going to adjust. Let's see, I think these were the I and J variables. Here is I and J where we're going to initialize them. Like I said, EBP is here, minus hex C is minus 12. So you're going to count up 12 to get to him. 10 is in decimal 16, so you're going to go up 16. So from here, this is 1, 2, 3, 4. 4 times 4, 16. Okay, I have to hit here. So from there's the first instruction going to adjust that. You see the constant 1 is in your frame. The next one. Now we're going to get ready for our call to that function sum, or actually I think here was myAdd. Putting it up. We should see that's putting the first variable up there, putting the next, call is a combination instruction. So those are the parameters to the function, by the way. The call is a kind of a combination. It's going to do a jump to and a push. And there you can see that. And now, this is the routine that it's going to go to. So this is the actual sum routine. And you can see here, this call is going to go to this address. At this address is the very beginning of that function. So now you're actually in the call. Once again, you're getting ready to change your frame. Doesn't really care what the stack pointer is here, but it's just moving it up so that it can have space to put its variables. Okay, so now we've actually done our calculation. You can see that our local variable is 3, right? That was the thing that we put up on the stack. So now when we do our leave, we're going to put that in EAX. And so here I believe I've shown you EAX already. Yes. So pulling it off of the stack, putting your EAX register, and that was what I was saying was the update there. The return is going to walk back down the stack. And once again, now we're back in the main routine, whereas we were in this routine here. And then this is like where we're going to be doing the push outside for the actual pushing to the library call. And what I was wanting to show you here is the difference between doing the call that was inside the routine versus doing the call to the library call. But it's the same kind of thing. You know, you're going to put stuff on the stack. You're going to pull them off, and let's see. I want to get it down to this. This address here, this is the address for the print specifier. If you remember when you saw the printf, it had the address, had the thing saying sum equals %d. That's a string. That's in memory. That's too big of a thing to sit in a register, so it has to go outside, right? So, and then once it's there, it's taken as printf, that function, pulling off what it's going to print, and then what the values from the stack. So if we do the dump of that address, you can see that, and if you remember that sum equals %d. You do the add. It comes back. It's telling you how many bytes it is. And then that would be it. After that, it would quit. And it's just like the return from the actual main routine. It's not of interest. So just before we do like a Linux demo here, I just want to say once again, the compiler takes a source, builds a sequence of opcodes. The assembly code is most primitive. You're going to be able to use special constructs because, like, you know, when you have code and you're saying, I'm going to do an if condition or a while condition, they all look the same. It's always the same. You know, it's not like random how it's going to determine what the assembly should be when it does like a loop construct. So I think here I'm just showing you how to set up GCC. The other nice thing is that by default, this old style of putting stuff in the stack frames and the registers, it doesn't do that anymore. Now it'll kind of short circuit that. But you can set the compiler options to go back to this style. What I'm saying is, the number of your parameters, it may not put all the parameters on the stack. Some of them will be in the registers. and then using your layouts to see a mix of assembly, and how I'm going to be using screenshots of my GDB session so that I can play things back in time. You know, when you're writing code and you're going through a debugger, it's kind of easy to get lost when you're following something, but you want to be able to back it up. And sometimes it's hard to back up because when you back up, things have changed. You know, you've already written to that memory location, right? But if you're getting snapshots, you can go back and you can look at it. You just have to make sure you take all the snapshots to see all the things that you might want to look at backwards in time later. So basically this is like using GDB. I'm using like set term to take the screenshots. And I'm going to show you how that I put together those snapshots to make those presentations that I did before. Like I said, so I think there I was showing you how to do, and this is like terrible, it's so small, but showing you what the setup looks like. I think it should show how the set term is being shown, and then how I'm just going back and forth. GDB is not running here. I'm just looking at what I did the snapshots with GDB. Think of it as, wow, you can do this with a text editor versus like, oh, I use IDA Pro. Well, you can't do that with IDA Pro. Once again, I realize you can't see that well back in the back, but I think you wanted to be able to look at this online, and then you could play and replay. And it works fine if you're sitting in a computer. So now we're going to step back a bit. We're going to look at Windows. And one of the things I want to show is how do you kind of look at it from a different perspective. It's going to take forever if you're trying to do something like this to find out what some code does. And it's not absolutely necessary. You know, you can find a lot of ideas about how a particular code works by looking at its behavior or looking at how it works in the system, what routines and DLLs does it use, etc. So here we're going to look at a portable executable. File format specification is online. MZ is in the signatures. You know, MZ is the author who came up with the specification, and it's at a certain byte. We're going to look at it with a hex editor, a portable executable viewer, and depends. And we'll try and tie this back to what we were seeing. And all of this is part of static analysis. Static analysis, if you're an analysis for doing pen testing or malware executables, you would use this term. But basically, it's like looking at a piece of code without running and trying to understand what it's doing at a high level. Looking at the dependencies, determining whether or not it has link time or runtime dependencies, looking at the strings and resources it's using, and looking at the hash of the executable. So, as an example of a hash, I saw a guy yesterday talking about virus total. I'm not sure everyone knows about virus total, but here's an example. Basically, you're going to take an executable, go to this website, enter the name of your executable, and it's going to look up. In this case, someone had already analyzed it, and it's going to say, oh, this executable is blah. Now, I don't know if they look at the entire executable and compute the hash, or if they look at just like the runtime section. But it's a good thing to just to play with if you have an executable and you don't know. It gives you an idea. Doesn't cost anything. And this is just a slide saying, okay, well, hey, you know, why would you care about looking at an executable with a tool. Well, I mean, here's an example of, in Windows, I have an executable. It looks to me like it's a bitmap, right? But when I click on it, I don't get a bitmap. Well, you know, it doesn't show me. But if I get a command prompt, you know, and I actually try to run the program, sure enough, something happens. And in this case, I think I was just trying to run like Notepad or something. I can't remember what that was. I just copied the file, changed the extension, whatever. It's trivial. But you could tell by doing some static analysis, either by looking at the executable with a hex editor, you would say, oh, this is not a bitmap. It has this MZ at the very beginning. You see the PE. You see the stub there. It's trivial, static analysis of identifying. You could look at it actually with PE view. It'll decode. It doesn't matter what the name is. And same thing. You can look at it with depends, and we're going to talk about depends later, and I think this is a good slide, but depends is a program that'll say, like, for a particular executable, the mysterious foo executable, what are all the modules that it uses at the first pass? And when we saw like the printf in that Linux demo, that comes from standard library, that would be, if this was Linux, you would have libc there, right? And then for a particular library, it's then going to show you in that library or DLL, what are the routines that are definitely by this level executable being used. And then for that library, what are all the possible entry points? And then I think this is just a list of all the modules. I'm interested in this one. And so like if you were to do an expansion, you could say like, oh, okay, this guy uses another one, and that one uses some more routines. And so you kind of get a feel for it. And based upon these, you can either look by ordinal or you can do by name. This is kind of key because you can use these addresses to know where I'm going to hook something. This is static. This is looking at the portable executable file. It's going by the sections, and it's saying, oh, okay, he here is importing this library. It's in the import section, and this is what he's using. So you don't have to, you know, so if you have this foo.exe, you don't actually have to run it at this point in time. That's the whole thing about this static analysis. So if on Windows, if you're going to determine the capabilities based upon just the DLL is included. If you see this one, you have a good idea that it's going to be registry work. If you're seeing this one, it's going to be doing process memory, file I/O. If you see any variants of this, MSVC runtime, MSC runtime with a number, or CPP, it's like the libc equivalent standard libraries. The CPP is just saying it's using the C++ versions instead of the C versions. Your NT, 9 out of 10 times, the executables aren't going to use those directly. Other DLLs use them, but there's some things there that it will use, and that's the kernel. If you see an executable that has a dependency on shell 32, that means it's a good chance it's going to be getting a shell prompt, command prompt, or executing a command prompt. User 32 may not really be that interested. It's the Windows user interface, but from that, you can then hook things to get you back in code. And then I guess like way back when, if I was looking at an executable, not so much to determine what it did, but reverse engineering it to change what it's doing, I would go by whatever I/O there is, and if it's a user interface, pop up, you know, a message box. It's like 9 out of 10 times that's what you're doing. You're going to go from there. Okay, you've got this message. How did you get that message? What was the sequence of events to generate that message? You'll see WinINet is high-level networking versus WinSock. So this would be things like HTTP. This would be things like opening a socket. So dynamic analysis. When you're running GDB, you're at the most lowest level of dynamic analysis. That's where you're actually running. But you probably do dynamic analysis all the time. Like, you probably ran like a registry monitor, or you've ran a file monitor. I want to install this program and see what it does. And so in this particular case, you're going to run the executable, but you're going to watch what the executable does in these particular types of tasks. So in order to run something, especially if it's an executable that you don't really know what it is, you don't want to take your development machine that you work on all the time and run some mystery executable, right? That's very threatening. So you want to try and use it in a VM. We're in the VM era now. It's great. And the nice thing about VMs is you can take a snapshot. You can say, okay, I'm going to set up my little Windows XP VM. I'm going to configure it so that I have networking from this VM to the same another VM on the same box. Networking is only going to go between the two. I'm going to run it here. I'll see the communications between the two machines. So I have like networking. I could see like, oh, he's opening a port. Oh, he's going to HTTP. Oh, he's trying to fetch this URL. What's going on? And if it downloads or tries to do something dangerous, it just affects that VM. And it's a snapshot. You can just roll it back. Who cares? I missed it the first time? Well, let me just roll back the snapshot, set my tools up a little differently, and do it again. So Procmon is a tool for this dynamic analysis on Windows. I don't know. Whoops. I don't think I have a video on this one per se. I don't. That's why it's going. But and that's a very small one. But what I'm trying to show here is I just have a simple batch file. And with this batch file, I'm going to execute, I believe it's a Python program which is accessing the disk. Within Procmon, I'm saying based upon all processes, I want to search for this particular process in this command prompt that's running in a loop. And I want to then filter by file I/O. So I could see, oh, this particular program is accessing these files on the file system. And that's kind of helpful, right? Like I run this program. Why is he touching something in the Windows directory? Why is he doing a write in particular? You can filter it down to reads and writes. This is a dependency example. And I think what we're going to do is we're going to use this same code again, which it's kind of hard to see. But the program that I took in Linux, which was that simple add, we're going to run it in Windows. And what I'm showing here is this is the debugger. It's showing the C lines in the debugger. Those are the bold lines. The stuff in between is the assembly. And then that particular executable, he doesn't have very many DLLs he's using. And for that one particular DLL, this routine here. And this is a very bad slide, I apologize. But if you sit in front of the computer, you could see it. But the key is we're going to look at that program in Windows some. This is a different one, and I think this one is more interesting. And I wanted to show this before I went on, because this particular program, one that I wrote, uses dynamic linking. So when you run this dependency, this kind of gets back to the question you said. You talked about, do you have to run something? You can set it up so that you have load time linking. So this executable, when he starts up, at load time, these are all the DLLs that I'm going to use. But you can also have it set up so that this program, when he starts up, he's going to try to run at runtime, find a DLL by name. Based upon that name, he's then going to use functions within it. So you wouldn't see it up here, right? Now, one of the things that you can keep in mind on a piece of malware or something trying to hide something is if you don't have a lot of DLL entry points being used statically, you got to think, why are they doing that? And that could be some key. But it does have to use particular routines like load library and get proc instance to do it. Those will show up. If you don't even have that, it's a packed executable. It's got some kind of compression. It's going to run, then it's going to decompress in memory, and then it's going to do it at runtime. Thought I had a slide here. Okay, I don't. What is this? This is, so, wow, I can't even see it from here. Simple, I think in this particular case, oh yeah, that's exactly what I'm showing here is, this is all the code that it takes to load a DLL, and then based upon here's the load of the DLL, which is sampled DLL, and then here's how I'm going to get the function pointer to a particular function in there. And from that, we can look at that as well. It's not that complex. Strings is another example of something that you can do, and I realize now this should have been in the static analysis section. Just running a strings on a program, seeing the strings that are there. If you see a URL in there, you have a good idea that he's doing something via the network. But that can also be used as how you're going to look for those function calls. Like, where's the function call that references that string? Yeah? I just used the strings program. I think all I did there was use like a GNU version. I'll tell you something about strings since we're on there, just curiosity. I worked on some code where it was more an exercise of just, and all of this, if you're trying to find down the malware guys or what they're doing, it's just layers and layers and layers of different protection, because eventually you could figure it out, and there's a way to do obfuscation of the string. So like if you looked, you wouldn't recognize any of the strings, and basically I'm going to scramble my strings at compile time, and then at runtime, I'm going to use the reverse. So right before I do that function call, I'm then going to decrypt that string, use it, and then that buffer in memory, I will encrypt back. And that way, statically, you would never see the strings in there that say fetch URL blah, 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 but you would be using a string eventually, right? So here, once again, we're going to use that same program. We're going to look at it with symbols. So this is not reverse engineering. This is just debugging. But I want to get you kind of in the feel for how it works, so that then we're going to go to a mixed mode, and then eventually we're going to go with no symbols. So this is in a VM on a Linux box. I'm just using the free 2008. I'm going to attach to a program. Because I'm attaching to it, by the way, it knows where it is. I think in this case, what I'm going to do is I'm going to hook on starting up a program and getting the dialogue, and based upon that, I can then go through the Windows message pump. And this is the switch. There's the dialog box. This is a call stack. So that's that frame that we saw on the right-hand side, but since we have symbols, it can tell what's going on. These are some variables. And I was just showing you, like, trivially simple, how we're going to look for that OK or cancel and what it's going to do with the, I believe we have, what's this one? Can't read it from here. Simple executable. I'm changing, okay, here I'm changing the EAX variable, so that's what's coming back. And I think that I was getting the result, and it's going to do something different. Got this terrible prep. That's so this is one with mixed C and assembly. That got smaller, should be getting bigger. So in this case, I took that sum program and I had it so it had a loop. So that's the same thing, and I just said, okay, we're going to do like a S random, we're going to get a value, and now we're just going to do this over and over, and we're going to change I and J. We've got some system calls, additional. We're making sure I and J are some values here. And we're just going to run this. And this is so that you have the executable and you can pause it and you can jump into it. So I think I do a clear screen. I'm starting it up. Oh, no, there I was looking at the strings. So I'm looking for that specifier in memory so that we know the address, right? So we're going to be looking for this. This is what we want to get to. The string is there. It's at a particular offset. We look and see when we're at that offset. So we're running. Now we're going to go back up to Dev Studio. We're going to attach to that process. That was the add.exe program we saw. And this is my stack frame. So like right here, I'm in a DLL that's not the actual executable, right? Because, you know, remember you saw the dependency, it goes down the chain, you can call something. And as I'm watching TV doing this, I'm just clicking OK, 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 till I see this show up as add. And I think I even missed this once. But basically this is the stack frame. This is the only thing I'm really looking at. I'm not looking at the registers. I'm just looking to see, as I pause the program, let it return from functions and step until I get in there. Just a few times. Okay, so now I'm in the add, and now I'm looking based upon these addresses. There's an address. I'm going to set up my, basically up here, I'm looking at the whole frame. Down here, I'm looking at the stack for a particular portion. I think I've got like EBP minus 128. So in Windows, it's got a little bit bigger frame, so I'm making it a little bit bigger. And that way I can see the X's showing up. I'm looking for that address. That's why I was highlighting it there. And I think this is the address that was there. There was our EAX. Those numbers and that EAX3 are as a result over here. So we're going to kind of patch this a little bit just to make it change. I think I'm going to bump it up to 11 just as a joke. But I believe this is like looking for the string itself. There it is. So now that 3 is going to be 11, which is actually 11 hex, so that would be 17. It's not really 11. And now you should start seeing this instead of being 3, be 11. I think I'm going to let it rip. Oh, okay, so I'm stepping just to show you, adjusting it a little at a time. And I may have missed it, but stepping out. Ah, okay, I remember when I did this. This is, I actually had an error here. I stepped too much, so I changed the wrong one, but it's going to come back, just 1 second, and it will do it. Once again, the key is making sure you're in the right DLL or right frame. So you don't want to be in these DLLs that you don't have source code and they are not the program. You're not going to be changing those. You're going to be changing the program that you're affecting here. Give it 1 second. So we've got it. Now we're going to look for the address. There's the 3. So there's the 11. There we're doing the EVP, not as quite as much. We want to see that we're actually making the change. This is pushing that result before we do the actual call. And I think this time we should see the 11 come out. So there's the 11. So once again, that's not like rocket scientist or anything, but basically I'm just trying to show you how you can use the debugger within Windows. That's free. And before we get, and I was just trying to show you that without, how you would go about without the source code, looking up the addresses that's coming from that string, knowing where to zero in on it. So I won't show you that again, but I will show you this. So, like I said, all this stuff is kind of hard, and you don't really need, I mean, when you're reverse engineering something, you're never going to know with 100% certainty what it's doing, because some guy was working with source, you're working just upon what the machine's doing. But you can get a good idea of what it's doing by looking at it from different angles. And one of the things that I think kind of is cool here is this, using the 2 VMs, using the iNet sim to run in a Linux VM, telling the Windows VM what websites their DNS resolve to. Oh, he's trying to run trying to fetch a web page. Well, let's see what web page he's fetching. And so this is just kind of showing you 2 VMs running side by side with iNet sim. So this is just showing you the iNet sim config file. The focus comes in as it begins to figure out what's going on. And I think I'm just showing what the address was. This is just I think this is a net SH script for showing how I'm going to set up the IP addresses on the Windows versus the Linux. So those are 2 VMs going step by step. And then I think it was, I think I did a ping or something there, but I won't replay it. And we're coming to an end. So we are at the end. So here's something I just want to say about this, and that is, you show all these things, you're like, oh, this is like 32-bit, we don't do 32-bit, we don't do 64-bit, and and people have all kinds of techniques they're going to use to prevent you from finding out what they're doing. For example, in this very last thing we saw, you could have code in there that could say, oh, if I'm on a VM, like the VM we just saw, I'm going to behave differently, right? Well, the thing is, if they have that in there, you can look for it. You could patch that out, right? They have things like anti-debugger. Oh, I'm in a debugger. Well, I'm going to start using the int13 to kind of like screw up their life and make it difficult for them when they're in the debugger. I'm going to be sending signals. If I'm in a debugger and he's just going to let something rip, you remember like we were in the frames and we're like saying run, 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 or return out of function as we're watching those frames. Well, that takes time, right? But if you were running at computer time, it was running outside the debugger, it would go by real quick. Well, you could have routines in there that would say, oh, I know how long it's going to take clock ticks or whatever, wall time, who knows, between these two bits of code. But if I'm in a debugger and somebody's playing around with it and single stepping it and the actual tick count goes up or wall time comes up, I'm in a debugger. So I'm not going to do the secret things that I want to do, right? I'm more into like what the debugger is going to do. So yeah, the problem is if you can't use the debugger to pull out the debugging stuff, you're going to use possibly a disassembler. But then you kind of run into the problem of, oh, they put in anti-disassembling type stuff. So if they have that case, you're going to have to go back to, let's go to an editor, like a hex editor. Just like you're saying, like you can go in, I'm not an expert, but you could go in based upon an offset and look for something there and just tweak it, make a 90. So, question. And the timing, is a debugger attached? One of those demos, one of the reasons why I put it up there was you could actually see there's Microsoft and their DLLs will have the ability to say, am I under control of a debugger? And you could see the system call actually up there. I wish I would have paid attention to it, but it was on the slide. You can also check out if you're attached to a debugger by looking at, I think it's the portable execution block or EOB block. It's like a system component that all executables have that the Microsoft Windows is going to maintain. You can do something as trivial as the output debug message. Some people like to, when they write code, instead of doing a printf to standard out, they would do this output debug message to a special output log. And then you can look at that log and you can get your results. It's like for messaging. Well, the code that doesn't want to know if it's under debug control could write to that, and if it returns back without exception, it's running, right? I mean, it's that trivial. Anti-disassembler, I didn't show a lot of disassembly stuff here, IDA Pro or Ollie Debug, but they are more like, you're going to analyze the code and you're going to look at it and you're going to try and trace it, and that's pretty cool. I mean, it's difficult. It's not something I do. I want to run into debugger so I can see what it's doing. There's just too much stuff going on. But what they will do to prevent you from being able to run or being able to look at it with a disassembler, and you can disassemble within the debugger, is the concept of linear versus flow. Linear is saying, okay, if it's well-written code and it's not written to be obfuscated or prevent tampering, like the code that I'm going to write, right? You're going to say, this is the start of my text segment where my executable goes, and now start disassembling at this address. And you go down, you go down, you go down, everything goes linear. Flow actually says, kind of as it's executing, if it was executing, what would it do? What would it look like? Well, so you're like, well, what's the difference? Well, you could, in a linear one, you could confuse the disassembler, which you could say, I'm going to take the code that was written by the compiler, which would work normally, right? And then I'm going to hand patch in a jump address that's going to jump into the middle of an instruction that would normally happen if it was complete linear. So like, you know, it's going to jump, say, to the third or the second octet of a 4-octet instruction. Well, after that, you're all going to be completely off by 1 byte from there on out. So the linear would miss that. A flow one, which is actually happening at runtime, it would pick that up. However, you can set up games of like, if you're going to do a flow, is it going to be the flow going through a branch this way or a flow through the branch this way? You know, as far as the disassembler goes, he's not keeping track of what's happening at runtime, so he would have to make both branches, but the actual code, the way it's performed, would always at runtime take this branch. So that's kind of interesting. Like I said, the virtual machines, you know, if you're running, you know, 2 VMs and you're going back and forth and you're able to run netcat or TCP dump to see what actual traffic is going on, well, they don't want you to be able to do that, right? They want to make you have your hooked up to a live network. They would look for those blobs. Obfuscation is things like string hiding, like I mentioned at the very earlier when we talked, but it's also like virtual machines. I mean, I'm not an expert by any stretch of imagination, but I'm a little bit comfortable with like Windows and Linux at C level. But if you were to go ask me like, hey man, what could you do with this Java? You know, because the Java is going to be running on top of the virtual machine, on top of that. I would say, well, what I'm going to do is I'm going to say, I don't know what it's doing in Java, but eventually it has to get to the C routines. I'll look at it there. But who knows? Maybe it could be setting up something in memory within that virtual machine instructions that would be awkward to find at the underlying C level. And then, yeah, I mean, that's it. I mean, if you saw, you know, let's even go back to the other, before we did this, let's go to the DLL. If you saw a DLL, it had no, very few imports, or its size on disk was much different from its size in memory, and it had, you could like look through it and you found 13 instructions in the disassembly, or when you did your disassembly, you saw like a warning like, hey, this is like inside of another instruction. I think IDA Pro will recognize that, the IDA Pro free, I think will recognize that immediately. And you saw things like, it's like looking for is debugger attached in VM artifacts. Like you saw something about the VMware network port. You'd be like, oh my God, this is like the heavy duty NSA. They pay money to write this malware, right? Yeah. So anyway, we're about done. I think we got like 3 slides left. So live patching, I did one at work recently, which I thought was cool. Fell on deaf ears, but I thought it was cool. But basically, 90 is a no-op and a jump. With these 2 things, you can patch stuff, right? You can say, okay, I'm running this code, I'm doing these, you know, compare. Based upon this compare, I'm going to do something. Well, I don't want to do that compare, right? But I don't want to have to, every time I run this in the, you know, in the debugger, you know, tweak that value to make that change. So I could just jump over it with a 90. The 90 makes that no op. Or I've got something that I actually want to rerun, or I want to, I want to keep the code there, but I know that I don't have this result, and I don't know exactly what it is, but I want to skip over this stuff. Well, you just do a jump, right? And then Ollie debug. I was showing like how you could do runtime using the same things. GDB is really where I do it quite frequently. And then, so the references, and I just want to put this up. I didn't come up with any of this stuff myself. Back in the early 90s, I worked at a company that had soft ice. We used it for Windows device drivers. And I don't know, I was like looking for like soft ice instruction manual or something. And I came upon this site and I was like, what is this guy? I was like, he's insane. But he had some like really good tutorials that, I mean, you couldn't do all the tutorials because the executables that he's showing you how to reverse engineer, you couldn't even get the copy of them. But in that case, he was like, how? This is in Windows, right? You have it basically boils down to set window text A, hook it in soft ice, and go from there. And then, I guess last summer, I got a copy of this book, and I thought this was a great book. And when I was reading it, I was like, I know you would know. I'm glad you're here. It makes me flattered that you're here. This is a very good book. These guys, I think they're from Fort Meade. I'm pretty sure. Huh? Okay. The thing I like about it is he is showing you how to do stuff. He talks about the static analysis, dynamic analysis. I didn't even know there was such a term. I thought it was just we're going to run a debugger, And he has labs in it, and you can follow along. When I was reading that, I was like, I'm not going to do a book report, but there's stuff here that would be good to give back to CarolinaCon, because I've learned some stuff here, and that's what I was trying to share with you guys. So anyway, buy this guy's book, and look at this. He has like a vodka martini up there you might like. So how are we doing on time? That's it. What time is it? 45? Time's up. Okay. Well, very good. Yeah, so, where is it? Oh, it's still up there, okay. I'll try and hit exit and do it again, because I think that would be easier than trying to go through 45 slides. Nope. Okay, let's try to go through 45 slides. Slide up, 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 Tonga. That's the presentation, sorry. If you go to www.skink.net, you can then look up NetSkink. And I think, I hate to say this, not all of this stuff is up there. The best thing to do is to go to that www.skink.net, S-K-I-N-K, like the little lizard. Look for presentations, and it would be, let me show you this little bit bigger text. Do I have it? Nope. Just www.skink, like right here, and look for presentations. The presentation is there. The stuff in GitHub, I was updating that, and then kind of along the way, I was like, I need to get the presentation out, and I may not have them updated. But my email's there. If you see something you want to talk about or get the source, I will make sure I update it up there. I think it was a good chance. I really enjoyed talking to you. I really enjoyed it. And like I said, I'm happy to be here at the Cargo Pants and Messenger Bag Meetup. Thank you.